Archimedes of Syracuse.
It's an amazing collection.
It really is. We're talking about a man who stands at the absolute intersection of, pure abstract thought and real-world, hands-on engineering.
It is an immense task to unpack his legacy.
Yeah.
Where do you even begin? Archimedes lived during the 3rd century BCE, a period often called the Golden Age of Greek mathematics.
Right, so he had contemporaries like Euclid, these foundational thinkers.
Exactly. But what truly sets Archimedes apart, and I think why he remains so relevant, is that he's often described as the world's first mathematical physicist, or mat physicist for short.
Meaning he wasn't content just to, muse philosophically about how the world works, which was pretty common for Greek thinkers back then. He didn't just speculate.
No, not at all. He took the rigorous abstract geometry, the pure math of his time, and he applied it with this just unprecedented precision to the physical, measurable world.
To things like levers, to fluids.
To the defense of an entire city.
Yeah.
He was creating universal laws out of everyday observations. It's really incredible.
And his achievement is still revered today. I just love this detail, the ultimate modern tribute. The Fields Medal.
The highest honor in mathematics.
Yep, the Nobel Prize equivalent for math. It has his portrait on it, and the inscription on that medal is it's magnificent. Transie sum pectus mundoque potiri.
Which means to surpass human nature and conquer the universe.
It's perfect.
It really is. It captures that sense of ambition and scope, which is exactly what we see in his work. He was quite literally trying to measure the cosmos while simultaneously finding ways to defend his home city against the greatest military power of his day.
And that's our mission for this deep dive. To really unpack his key laws, like the law of the lever in hydrostatics, explore his boundary-pushing mathematics, from approximating pi to inventing new ways to write giant numbers, and of course dissect the incredible, sometimes legendary machines he built.
From the iron claw to that unbelievable mechanical planetarium.
We're going to try to separate the mathematical genius from the historical mythology. So let's start with the man himself. When you look at the sheer volume and, the sophistication of his surviving technical works, his geometry, his proofs, it is just staggering.
It's mind-boggling.
But at the same time, we know so frustratingly little about his actual life. It seems like he left behind the blueprints of the universe, but, forgot to write his memoir.
That's the perfect way to put it. He absolutely prioritized the work over the narrative. We estimate his birth around 287 BCE, and that's based on accounts from later Byzantine chroniclers, like a writer named Cece. He suggested Archimedes was about 75 when he died. But that death date, 212 BCE, that's the single most reliable fixed anchor point in his entire biography.
And that's the day Syracuse fell to Rome.
Exactly. And the world he was born into was just defined by this perpetual conflict, the titanic struggles between Rome and Carthage.
The Punic Wars.
Yep, the Punic Wars, which shaped the Mediterranean for over a century. And Syracuse, on the strategically vital island of Sicily, was constantly trying to navigate between these massive geopolitical forces.
So he lived through the first two of those wars.
He did, and crucially, he was born into the aristocracy. He was related to, and a protege of, Hiero II, the tyrant of Syracuse.
Who had a really long and stable reign, didn't he?
Exceptionally long, 54 years. And this connection was, I think, essential. It afforded him the luxury of dedicating his life entirely to abstract research. He wasn't, working to feed himself. He was working to satisfy his monumental curiosity.
That royal patronage must have been his ticket to the big leagues, intellectually speaking. It let him engage with the greatest scientific network of the Hellenistic world.
Oh, absolutely. The intellectual heart of the age.
The
Library of Alexandria.
That's the one.
He corresponded frequently with the intellectual heavyweights of the time. We know he dedicated his more popular work, The Sand Reckoner, to Hiero's son, Gelon. And we have records of his exchanges with his friend Conan of Samos.
But the big connection was with Alexandria.
The most important connection was with Eratosthenes of Cyrene, who is the keeper of the Library of Alexandria.
Eratosthenes. Isn't he the guy famous for his remarkably accurate calculation of the Earth's circumference?
That's him.
Using just shadows and geometry between two cities. It's incredible.
It is. And the fact that he was corresponding with Eratosthenes, whose calculation for the Earth's radius, by the way, was within 2% of the modern value, it just shows you the level of intellectual sophistication Archimedes was operating at. He also sent many of his completed treatises, like On the Sphere and Cylinder, to another Alexandrian scholar named Dositheus of Pelusium. This was basically how his complex ideas were peer-reviewed and then spread across the Greek world.
So all that abstract geometry and pure research, it eventually comes head-to-head with political reality, right? During the Second Punic War.
It does. Syracuse makes a bad call and breaks its treaty with Rome, which leads to the infamous siege starting in 213 BCE.
And Rome does not mess around.
No, they sent their best commander, Marcus Claudius Marcellus. He was an experienced warrior who fully expected a quick, decisive victory. The Roman fleet was massive. They brought forward these enormous siege towers mounted on ships, they called them sambucas, designed to just completely overwhelm the city's defenses.
But the siege was famously held off for 18 months, and not by the sheer strength of the Syracusan army.
No, it was held off by the application of advanced mathematics turned into weaponry by one man.
Marcellus must have been furious.
He was utterly humiliated. The attacks just dissolved. Polybius, who is one of our most reliable sources, describes Archimedes setting up machines that could fire projectiles, giant stones, lead slugs to any desired distance.
So he had range control.
Perfect range control. The minute the Roman ships drew near, they were struck by smaller, hidden, short-range machines that would suddenly drop massive logs and stones right over the battlements, smashing the deck and all their siege equipment.
That sounds like psychological warfare as much as it is physical defense. The Romans couldn't even see the engineer, just the devastating results of his physics.
That's the key. The machines were unseen and perfectly adapted to the distance of the approaching fleet. Marcellus was described as being astonished by this continuous hail of destruction.
I bet he was.
He soon realized that dealing with a single mathematician was a greater challenge than capturing the entire city. He eventually paid Archimedes the ultimate compliment, calling him Briareus among geometers.
Briareus, the hundred-handed giant from mythology.
Exactly. This tells you that the machines felt supernatural, overwhelming, and just completely unstoppable to the Romans.
But despite Archimedes' genius, the defense ultimately failed. So how did Syracuse fall after holding off the Roman might for a year and a half?
Well, most sources suggest the city was taken by cunning rather than by brute force. In 212 BCE, the city was celebrating a major festival for the goddess Artemis.
A bad time to party.
A very bad time. The guards were incapacitated by wine and revelry, and they were taken completely by surprise. And it was likely aided by some betrayal from within the city. Once the walls were breached, the Roman sacking was swift and brutal.
And this brings us to that most poignant, legendary scene of his life and his death. The scholar is so absorbed in his thought that he ignores the chaos of the city falling around him.
It's the ultimate image of the intellectual martyr, isn't it? The traditional story, which gets reinforced by Roman historians, is that a common Roman soldier came upon Archimedes while he was just completely engrossed in solving a geometrical problem, drawing figures in the dust or maybe on a board.
And he refused to stop.
He refused to interrupt his work until he'd completed his proof.
Which gives us those famous, though probably alleged, last words. "Do not touch my circles."
They capture that obsession perfectly. He prioritized the abstract problem over his own immediate self-preservation. And while the soldier acted against orders, Marcellus had specifically commanded that Archimedes be taken alive. The event just cemented his image for all time.
Did Marcellus react to the news?
He was genuinely distressed. The sources say he turned away with contempt from the soldier who delivered the blow and made sure that Archimedes' family was treated with respect.
That respect, even from the conquering general, it really solidified his unique persona for posterity. Roman writers like Plutarch painted him as the quintessential absent-minded scientist.
Plutarch's description is incredibly vivid. It really underscores the difference between how the Greeks viewed pure intellect versus practical engineering. He writes that Archimedes was constantly in a state of contemplation, so much so that he would neglect food and personal care.
His servants had to drag him to the bath.
Literally. They often had to physically drag him to the public baths. And even there, he couldn't stop thinking.
Of course not.
Right. Plutarch describes Archimedes drawing geometrical figures, sometimes in the hearth ash, or even drawing lines on his own body after it had been rubbed with oil for bathing.
Wow.
This constant physical compulsion to solve the geometrical problem speaks volumes. It reinforced the philosophical bias of the time. Pure geometry was noble, while mechanical application was considered, mere manual labor technique and unworthy of serious study.
So in that view, the war machines were just a hobby.
Exactly. According to this view, Archimedes only built his magnificent machines as amusements of geometry just to please his relative, King Hiero.
But the most concrete insight into his mathematical priorities comes from his final, very precise request about his epitaph.
Yes. He requested that his tomb bear the image of a sphere inscribed within a cylinder. This was the geometrical representation of what he personally considered his most beautiful and important discovery. The fact that the volume and surface area of the sphere are in an exact 2:3 ratio to the volume and surface area of the cylinder that encloses it.
To choose a geometric proof over his name or his military feats, that tells you everything about where his heart lay.
It was his proudest moment, a synthesis of elegant geometry. And this specific, highly technical request is actually what allowed the Roman orator and statesman Cicero to find the tomb decades later.
Right, Cicero was a government official in Sicily, around 80 BCE, so more than a century after Archimedes died?
About 130 years later, he was searching for the tomb, which had already fallen into complete oblivion among the locals.
They'd already forgotten him.
Completely. Cicero described finding the tomb heavily damaged, overgrown with brambles, and forgotten outside the city gates. He said that he identified it solely by that precise geometric drawing, the sphere and the cylinder, which was still visible, though heavily worn.
The irony is just striking. The great Syracusan mathematician, whose genius single-handedly defied the Roman army, was forgotten by his own people within a century.
And his tomb was only rediscovered by a visiting Roman conqueror who happened to share an admiration for mathematics.
And today, the tomb is lost again. All we have is Cicero's account of its rediscovery, a very fitting kind of paradoxical end to the story of a man whose legacy is defined by universal laws, not physical monuments. Okay, let's move to the bedrock of his physics, because Archimedes took these practical realities of mechanical advantage, using a lever, observing how things float, and he lifted them into the realm of universal law through geometry.
That transformation is the absolute essence of mathematical physics. Before Archimedes, people used levers, of course, but their understanding of why they worked was based mostly on empirical observation or, vague principles.
It just works.
It just works. Archimedes was the first to successfully apply advanced Euclidean geometry to physical phenomena and derive universal, mathematically provable laws from them.
So let's start with the law of the lever. The famous formulation is that forces and distances from the fulcrum are inversely proportional. But the conceptual revolution here wasn't just stating that law, it was the way he proved it.
Precisely. His proof was groundbreaking because he refused to limit his result to simple, easy-to-measure ratios. He proved the inverse proportionality of weight and distance from the fulcrum, even for incommensurable ratios.
What we would now call irrational numbers.
Exactly. Ratios that can't be expressed as simple integers or fractions. That required an immense amount of geometrical sophistication.
And this is where we see the necessity of abstraction, which is really the core of modern scientific modeling. He couldn't just analyze a real-world, messy wooden beam.
He had to invent a simplified ideal model, so he introduced the revolutionary concept of the center of gravity, or CG.
Okay.
He defined it as a single abstract point where the entire weight of a body can be considered to concentrate without changing its equilibrium. He then treated the lever itself as a mathematically perfect massless beam, and the weights as point masses concentrated at that CG.
So he's liberating physics from the constraints of observing messy reality and allowing it to be analyzed using the perfection of geometry. That is a huge conceptual leap, an insight into the power of ideal models.
It fundamentally shifted how you approach physical problems. By abstracting the mechanism, he could use deductive logic geometry to prove a physical result. And this process of using ideal models like massless strings, frictionless pulleys, ideal fluids, it's still foundational to classical mechanics today.
And this conceptual power led directly to that famous bombastic declaration often attributed to the lever law. Give me a point of support and I will move the earth.
It is the ultimate expression of the power of mechanical advantage. A small force can overcome an immense weight if the lever arm is long enough. But if you just pause for a moment and appreciate the sheer scale of that concept, it's thrilling. He understood that mathematically, there was no limit to the force amplification.
And yet, if we actually apply the math to reality, the practical impossibility becomes pretty clear.
Oh, absolutely. I mean, if we assume Archimedes applied, say, 60 kilograms of force, and the Earth was hypothetically 1 meter away from the fulcrum, the required length of his lever arm would be astronomical.
We're talking light years.
A length that would take hundreds of billions of years just to move the Earth by a minuscule amount. So the quote isn't about practical engineering, it's about the revolutionary scope of his theoretical understanding. It's demonstrating the universal potential contained within his mathematical proof.
Okay, from levers, we have to turn to the most famous single moment in his life. the realization that solved King Hiero's crown problem.
Right. King Hiero II, his patron, suspected that his goldsmith had mixed cheaper silver into a newly crafted golden crown. So he gave Archimedes the difficult task of determining the mixture without damaging the crown.
And he was completely stumped.
Totally stumped. Until, of course, he stepped into the public path.
The eureka moment.
The famous story, first recorded by Vitruvius, is that Archimedes noticed the water level rising as he submerged himself. He realized that the volume of his body was exactly equal to the volume of water displaced, and volume displacement. That was the key to solving the crown problem.
And that leads to the legendary dash through the streets of Syracuse.
Running naked and shouting, "Eureka!"
I'd have found it!
And what he had found is now known as Archimedes' principle, the law of hydrostatics.
Can you break that down for us?
It states that a body wholly or partially immersed in a fluid experiences an upward buoyant force that is exactly equal to the weight of the fluid displaced by the body.
To formalize this, he had to introduce concepts that weren't just, standard philosophical topics.
Right. He needed the concept of density, or specific weight, to explain buoyancy. Since silver is less dense than gold, a given weight of silver occupies a larger volume.
So if the crown contained silver, it would have to be bigger than a pure gold ingot of the same weight.
And thus, it would displace more water. And while he didn't use the Newtonian term force, as we understand it now, he was fundamentally working with buoyant force, displacement volume, and mass, establishing the framework for fluid mechanics centuries later.
Okay, so now we need to address the central problem with the legend. The method described by Vitruvius, which involved measuring the overflow of water, is almost certainly flawed when you look at the precision required.
It is scientifically very questionable. The legendary method says Archimedes would have measured the volume of water displaced by 3 equal weight items: a gold ingot, a silver ingot, and the crown. The gold ingot displaces the least, the silver the most.
And the suspect crown would be somewhere in between.
Exactly. But the problem is, why does this measurement technique fail?
The difference in volume is minuscule, right?
It's tiny. Let's just run the numbers. Assume the crown weighed 1,000 grams and was generously 30% adulterated with silver. Gold has a density of about 19.3 grams per cubic centimeter, and silver is about 10.5. A pure gold ingot would displace about 51.8 cubic centimeters. The mixed crown would displace about 64.8 cubic centimeters.
So that's only a 13 cubic centimeter difference. That's, the volume of 2 sugar cubes?
Exactly. And if Archimedes had used a typical ancient measuring vessel, say a cylinder 20 centimeters in diameter, that 13 cubic centimeter difference in displaced volume would cause the water level to rise by less than half a millimeter.
Half a millimeter. Trying to measure that accurately in the 3rd century BCE, dealing with the meniscus of the water, probably unstable measuring devices, that sounds impossible.
It was far beyond the precision limits of ancient technology. Even with a sophisticated water clock, a clepsydra, the issue is the visual measurement of that tiny volume change. And this is why later thinkers, most notably Galileo, concluded that if the eureka moment was real, Archimedes must have used a far more elegant solution.
A mechanical solution.
One rooted in his true expertise, the law of the lever.
So tell us about the hydrostatic balance method which Galileo championed.
Galileo suggested Archimedes used a method that was, in his words, far more delicate. It employs a simple lever balance. A scale. You have the king's crown and a pure gold ingot of identical weight suspended from opposite sides.
Okay, so they're balanced perfectly in the air.
Perfectly balanced. Then you submerge both of them simultaneously in a container of water.
So instead of trying to measure tiny volumes, he's measuring the apparent weight difference in the water.
Exactly. Since the crown, because it contains the lighter silver, has a larger overall volume, it experiences a greater buoyant force. Since that buoyant force directly counteracts the object's weight, the crown loses more of its apparent weight in the water than the pure gold ingot does.
So the scale, which was perfectly balanced, instantly tips down toward the denser pure gold ingot once they're underwater.
It tips down immediately. The fraud is proven without having to collect a single drop of overflowing water or measure those minute half-millimeter changes. This method is instantaneous, highly visible, and it uses his primary mathematical triumph, the lever, to solve the problem. It just has far greater credibility than the Vitruvius anecdote.
And the principle of buoyancy didn't just solve a royal jewelry dispute. It gave us the fundamental rules for why things float or sink.
He established the foundational rule. A body floats if its average density is less than the fluid's density, and it sinks if it's greater. This rule has crucial implications, even for the fluid itself, particularly water.
Which leads to the strange physics of the iceberg anomaly.
Right, water is one of the few substances where the solid state is less dense than the liquid state. Ice is less dense than liquid water, which allows it to float. And if you calculate the ratio, the density of ice to liquid seawater, you find that the submerged portion of an iceberg is about 89%.
So the cliche is true. Roughly 90% of an iceberg really is hidden beneath the surface.
It really is. And this same principle explains how steel ships, which use a material far denser than water, can possibly float.
It's all about average density.
That's the genius of naval architecture, and it's rooted in Archimedes' law. It's not the density of the steel that matters, but the average density of the entire vessel, which includes that massive volume of air-filled cavities within the hull. As long as that average density stays less than the water's density, it floats.
Like with the sinking of the Titanic.
The classic example. The ship didn't sink because it was too heavy. It sank because when the hull was breached, water, which is much denser than air, replaced the air in those cavities. That increased the average density of the vessel until it surpassed the density of the seawater, and down it went.
And he applied these principles himself when he designed that massive 55-meter-long ship, the Syracusia, for Hiero II. Even that huge vessel had to be designed to keep its average density low.
Absolutely. The principles he discovered in the bathtub have dictated the structure of every great ship built since. It just shows the incredible durability of a law derived from abstract geometry and precise observation.
We've established that Archimedes' true passion was pure mathematics. While the Eurekas and the war machines made him famous, his geometry is what he felt was worthy of his eternal remembrance.
His surviving treatises are a testament to his ambition to solve the most difficult problems of his age. He wasn't just working with circles and squares, he invented new figures, like the spiral that bears his name, and pioneered methods for measurement that were centuries ahead of their time.
Well, let's talk about pi. The great philosophical challenge for Greek mathematics was dealing with curves and these incommensurable or irrational numbers. So how did Archimedes tackle the ratio of a circle's circumference to its diameter, pi?
He perfected something called the method of exhaustion. It's a technique that was initially conceived by Eudoxus and used by Euclid, and it's the direct conceptual ancestor of integral calculus.
So how does it work?
It involved finding the area or circumference of a curve by creating two boundary shapes. Polygons inscribed inside the curve, and polygons described outside the curve.
And the more sides these polygons have, the closer they exhaust the space between them, giving you increasingly precise upper and lower bounds for the curve.
It's brilliant. To calculate pi, Archimedes started with a simple hexagon inscribed and circumscribed around a circle. He then painstakingly doubled the number of sides over and over again.
From 6 to 12, 12 to 24.
0.24 to 48, and finally 48 to 96 sides.
That must have been an absolutely monumental calculation, especially given the lack of Arabic numerals or any kind of standardized arithmetic notation.
It was an incredible feat of numerical fortitude. By calculating the perimeter of the 96-sided inscribed polygon, he found a lower limit for the circumference. By calculating the perimeter of the 96-sided circumscribed polygon, he found the upper limit.
And what was the final result he rigorously proved?
He demonstrated that pi must lie between 3 plus 10 over 71 and 3 plus 1 over 7.
Numerically, that translates to pi being between about 3.1408 and 3.1429.
Yes, which provided an accuracy of pi to two precise decimal places, 3.14. And this approximation was the standard used by mathematicians and engineers for well over 1,000 years. It just speaks to the absolute rigor of his method.
So let's circle back to the discovery he requested for his tomb, that 2:3 ratio of the sphere and its circumscribing cylinder. Why was that result so significant to him?
I think it embodied perfection and elegant simplicity. In his treatise on the sphere and cylinder, he proved that the sphere occupies exactly 2/3 of the volume of the cylinder that perfectly contains it, and its surface area is also exactly 2/3 of the cylinder's surface area.
It's a synthesis of all these complex results into one beautiful, simple ratio.
It is, and to get there, he had to prove several supporting theorems that were themselves revolutionary. For example, he demonstrated that the surface area of any sphere is exactly 4 times the area of its great circle, the cross-section through its center.
Which gives us the formula 4 pi r squared.
Exactly. He also proved that the volume of a sphere is 4 times the volume of a cone with the same radius and height, which yields 4 over 3 pi r cubed. The 2:3 ratio was the culmination of all these individual, profound, geometric insights.
This is where we see Archimedes truly leaving his era behind and glimpsing concepts that Newton and Leibniz would formalize nearly 2 millennia later. He was basically performing integration before the concept even existed.
Yes, and the crucial evidence for this wasn't fully understood until the 20th century. For years, the scholarly world relied on works like On the Quadrature of the Parabola. But in 1906, a document called the Archimedes palimpsest was rediscovered.
A palimpsest, that's where they scrape off an old text to reuse the parchment, right?
Exactly. It was a Byzantine prayer book from the 12th century. And crucially, it was written on parchment that had previously been used for other texts. Through advanced imaging techniques, the scraped-off texts were revealed to be unique copies of Archimedes' work,
Including a really important one.
a vital treatise called The Method of Mechanical Theorems.
And what did the method reveal about his process?
It revealed his method of discovery. He actually confessed that he often used the law of the lever, a mechanical principle, to find the areas and volumes of complex shapes first. How would you do that? He would balance infinitesimally thin slices, which he called indivisibles, of the curved shape against slices of a simpler shape, like a triangle, to derive the area. Only after he found the answer mechanically did he go back and provide the formal, rigorous geometrical proof using the method of exhaustion.
So he explicitly said that finding the answer first made the geometric proof much easier. This is the difference between a philosophical result and a real engineering process.
It's the core of integration. He was, in essence, summing up infinitesimal slices to find a total area or volume. The most famous application of this approach was the quadrature of the parabola.
How did he tackle the area of a parabolic segment?
He proved that the area contained by any segment of a parabola is exactly 4/3 the area of the largest triangle that can be inscribed within that same segment. And to prove this, he implicitly performed the summation of an infinite geometric series.
So he started with the largest triangle and then added a smaller triangle in the remaining space and then a smaller one in that remaining space, shrinking on and on to infinity.
Exactly. The series he effectively summed was a plus a divided by 4 plus a divided by 16 plus a divided by 64 and so on, where a is the area of that first largest inscribed triangle.
And it converges.
By finding that this infinite sum converged perfectly to a finite number 43a, he provided a direct mathematical rebuttal to philosophical roadblocks like Zeno's paradoxes, which had implied that motion or the summation of infinite segments was impossible. Archimedes showed that an infinite collection of ever-shrinking parts can in fact result in a finite, definable number.
So from the infinitesimally small divisions required for calculus, he swings to the astronomically large with the sand reckoner. This was his only true work of popular science, right?
It was. He dedicated it to his patron son, Galen. And the purpose of this work was profoundly important for both mathematics and cosmology. He wanted to address the question of whether the number of grains of sand required to fill the entire universe was infinite.
A question many Greek philosophers believed was just unanswerable.
And Archimedes set out to prove it was not only finite, but calculable.
To do this, he needed a definition of the universe, and he actually relied on the most radical cosmology of his day.
He did. He used the heliocentric model proposed by his contemporary Aristarchus of Samos, the theory that the Earth revolves around the sun. This was highly unpopular at the time, but Archimedes needed the largest possible cosmological model to make his calculation a real challenge.
And even using Aristarchus's gigantic model, he proved the number of grains was finite. What was his astonishing estimate?
He estimated the total number of grains needed to fill this vast heliocentric universe was 10 to the power of 63.
10, with 63 zeros. How on earth did a Greek mathematician, using a numbering system that basically struggled once you got to 10,000, a myriad manage to write, much less calculate, a number like that?
He had to invent a completely new system of notation. The traditional Greek system, which was based on letters and myriads, it just broke down rapidly. So Archimedes invented a system based on myriads of myriads, or 10 to the power of 8.
And he built on that.
He designated this as the first octad. He then defined the concept of orders and periods, which allowed him to express numbers far, far exceeding anything previously conceived.
He essentially invented a form of exponential notation for the express purpose of managing gigantic numbers.
Precisely. His system could ultimately write numbers up to 10 to the power of 80 trillion. So the sand reckoner confirms his absolute mastery not only of abstract geometry, but also of pure numeracy, providing a foundation for how we handle astronomical scales today.
We have to return to the paradox now. The man who believed pure thought was superior to mechanics, yet whose practical inventions dominated the battlefield and shaped engineering for millennia.
It's the great contradiction of his life, isn't it? He only engaged in engineering at the insistence of King Hiero II, who wanted to make the power of geometry visible to the masses. But when he did engage, he applied the full force of his mathematical genius.
We know his defense of Syracuse held Marcellus at bay for 18 months. What was the engineering core of his military arsenal?
Well, he refined existing weaponry. He enhanced ballistas and catapults to a new level of efficiency. Sources note his catapults could hurl stones with incredible accuracy over unprecedented distances, which made the Romans vulnerable long before they even reached the walls.
But the most psychologically devastating weapon had to be the manus feria, the iron claw.
The iron claw was mounted on the city wall and worked on the principle of amplified force, basically demonstrating the law of the lever on a massive scale.
How did it work?
It used the principle of the block and tackle system, or polyplastos. It was powered by capstans operated by men or animals hidden behind the ramparts. This simple machine is a force multiplier. It allows a small input force to lift an immensely heavy load by increasing the rope travel distance.
And the claw would suddenly drop down, seize the bow of a Roman ship, and then hoist it violently into the air.
The sources, like Polybius, describe ships being lifted and then just dropped onto the rocks below, causing them to shatter. Now that description might sound a little exaggerated.
Yeah, it sounds impossible for an ancient device to lift a 500-ton warship entirely out of the water.
Right, but the required action was much simpler than that. The real goal wasn't to lift it completely.
What was the goal then?
It only needed to tilt the ship's bow high enough to destabilize the vessel. Once it was tilted, water would flood the exposed stern or the oar ports, causing the ship to capsize and sink under its own weight.
Ah, I see.
Modern reconstruction experiments have confirmed that this limited but terrifying action was entirely feasible. And the psychological effect of seeing their own ships manipulated and destroyed by an unseen mechanism was so intense that Roman soldiers would reportedly flee if they saw so much as a piece of rope swinging above the wall.
Okay, from the proven iron claw to the most famous military myth, the heat ray or the burning mirrors, did he use concentrated solar energy to set the Roman fleet ablaze?
Historically, this story is dubious. The most reliable contemporary accounts, especially Polybius, they detail the iron claw and the catapults, but make no mention whatsoever of fire mirrors. The story only appears centuries later in secondary, often less reliable, Byzantine texts.
So why do later sources insist on it? Where did it come from?
The story likely originated from his lost theoretical work on optics, a book called Catoptrica. He certainly studied reflection and focusing, and it's possible that experimental rumors about his theoretical work just morphed into a military legend over time.
But the scientific debate about its feasibility has intrigued thinkers for centuries. I know Descartes denied it in the 17th century, arguing that constructing a single, massive, precise mirror was just impossible.
And then, in 1747, the Comte de Buffon proved the technical possibility. He argued that Archimedes would not have needed a single parabolic mirror. Instead, he could have used a compound system of many smaller, flat, individually adjustable mirrors, a helioconcentrator.
He built one.
Buffon built an apparatus using 168 small mirrors and successfully ignited wood at a distance of 50 meters.
So the physics works, but was it practical for combat?
And that's the crucial distinction. Modern tests, including extensive recreations, have all concluded that while it's technically possible under optimal conditions, perfectly bright Mediterranean sun, motionless ships, and specific coastal exposure, it was simply too impractical and unreliable for sustained use in a real battle.
Right. Why rely on a ray of light when you have proven, reliable catapults and an iron claw that works regardless of cloud cover?
Exactly. The legend endures because it just perfectly captures his reputation for being able to command the forces of nature itself.
Beyond war, his constructive mechanisms continue to influence daily life even today.
The Archimedes screw, or cockley, is the prime example. It's a helical device for lifting water, and while the underlying principle might have been known earlier, Archimedes certainly popularized or perfected its design.
And it was used everywhere.
Extensively. For large-scale drainage, including dewatering the vast hull of the Syracusia ship, and it was later adopted for irrigation and for draining mines in Spain.
But perhaps his most complex and, breathtaking construction was the mechanical planetarium, or celestial globe.
This was the ultimate fusion of his astronomy, his mathematics, and his engineering. It was described vividly by Cicero, who actually saw the device after it was brought back to Rome as a war trophy.
And what did it do?
It was a sophisticated mechanism that displayed the synchronized complex motions of the sun, the moon, and the 5 known planets. It even accurately calculated the phases of the moon.
Cicero was blown away. He stated that the scientist who built it possessed a genius greater than any other human genius.
Well, the mechanism was driven by incredibly complex multi-stage gear trains. To synchronize the various orbits, including the highly irregular lunar path, it would have required a deep understanding of epicyclic and differential gearing. It demonstrated his practical mastery over kinematic geometry.
It sounds almost too advanced for the 3rd century BCE.
It did, until the discovery of the Antikythera mechanism.
The astronomical computer from the shipwreck.
Right. This astronomical calculator, recovered from a shipwreck and dating to the 1st century BCE, is a marvel of complex bronze gearing. Its existence confirms that highly intricate geared astronomy devices were indeed built in the Hellenistic world. And many experts now believe the Antikythera mechanism was a descendant or application of Archimedes' theoretical work, possibly based on his lost designs for that mechanical globe.
So it transforms the planetarium from a mythical trophy into a tangible ancestor of clockwork and modern calculating machines. As we close this deep dive, the scope of Archimedes' mind is just. It's truly humbling. We've seen him grapple with the infinitesimally small in calculus and the astronomically large in the sand reckoner, all while laying the foundations for mechanics, hydrostatics, and engineering.
His enduring contribution, though, I think, is his scientific method. He consistently sought to prove his assertions using rigorous abstract mathematics. He perfected the process of taking a chaotic physical reality, a lever, a floating body, and abstracting it into an ideal, mathematically perfect model.
The massless beam, the ideal fluid.
Exactly. And by doing so, he derived universal laws that hold true across time and space. That transition from observation to mathematical law is the bedrock of all modern scientific inquiry.
It is the moment the mathematical physicist was born. And even the legendary aspects of his life prove this point. I mean, the discussion about the burning mirrors showed us that his theoretical idea became a practical reality centuries later in the form of solar thermal technology.
Which leaves us with a final provocative thought for you to consider. Archimedes attempted to solve the 3 great construction problems of antiquity, including squaring the circle, creating a square with the same area as a given circle, using only a compass and a straight edge.
Which was later proven to be geometrically impossible under those specific rules.
Right. But Archimedes found a solution using his spiral, which required a different method. Kinematics, or the study of motion.
He bent the rules.
He did. His methods opened doors that his own philosophical constraints prevented him from fully walking through. So the question is, what other problems Archimedes solved by bending the rules of geometry might still be waiting for us to fully explore and apply using modern kinematic geometry, advanced numerical analysis, or engineering applications that he simply couldn't possess.
The genius of Archimedes wasn't just in the answers he found, but in the new rules he established for asking the questions. A truly timeless mind whose work continues to inform discovery today.
Join us and keep your curiosity well fed. Who knows? The next video might be exactly what you didn't know you needed.